This presentation is about our experience building a product using a serverless architecture, including tips and lessons learned for anyone who is curious about serverless. Some of the content gets pretty technical, but I hope anyone who's responsible for building or maintaining digital products can gain something from this. I'm Bobby Pantall from CC Pace. I've been developing apps on various platforms for over 20 years, and I'm interested in tools and technologies that make it easier to deliver interesting products to our customers. So how do you go from an idea to a working digital product in a fast and secure manner where you can focus on the aspects of the product that are unique to your problem? And importantly, something that doesn't incur a high fixed cost while you try and establish a market for your product. The COVID-19 pandemic caused major disruptions to how teams function in the workplace, at sporting events, and in academic settings. We recognized the need for a platform that could help teams function safely and efficiently when they return to in-person activities. It includes health symptom screening, compliance monitoring, notifications to isolate sick team members quickly, and digital contact tracing. It's within the context of this platform that I want to discuss our experience with serverless. We spent the summer and fall of 2020 developing a platform that makes it easier for organizations to meet the challenges related to the pandemic. We worked with epidemiology and engineering experts from George Mason University to design a solution that focuses on safety, efficiency, and privacy. We call it Pass to Play. My goal for this presentation is to describe how we built this platform using a serverless architecture, specifically in the Amazon cloud. I'll describe the lessons learned from this effort in the context of the Pass to Play platform. First, it helps to understand the primary components of the system. This includes a mobile app and web app for symptom screening and compliance checking, automated reminders for members to fill out their questionnaires at predefined intervals, an admin web dashboard to manage member health status, compliance tracking and contact tracing, card holder devices that track contact between members based on distance and length of time, and a Wi-Fi hub that transmits contact data from the card holder devices. Finally, the crux of our serverless solution is an API backend that centralizes storage and compute for the entire platform. Later, I'll show how all of these things interact. So why do we choose serverless? One reason is that we simply wanted to learn more about the capabilities of this architecture, including the various Amazon services and resources. But that's not the primary reason. There are many aspects of this effort that follow a startup approach. What I mean by that is we wanted to get something quickly built and available so we could test the viability of the platform, not to mention the natural urgency of the pandemic. So we wanted to focus on delivering business value rather than building infrastructure. Naturally, we wanted it to be fast, but we also wanted to quickly respond to a rapidly changing environment or problem domain. We wanted to avoid provisioning more resources than necessary. We didn't know how many customers we'd have, so why pay for the extra overhead? We followed the DevOps mantra of automating as much as possible. With cloud platforms, every resource and service is treated as code. This allows for rapid and repeatable deployments. Here's a high-level view of our solution. One thing to note is that with a serverless architecture, your logical design closely matches your physical architecture. In the past, you diagrammed physical or virtual machines that performed multiple tasks, such as web servers, database servers, queue servers, load balancers, maybe even down to the firewall level. We have abstracted those tasks into a set of managed services. We don't know the architecture of the physical machines because we don't care about it. We just need to know what services accomplish various compute and storage tasks. In this diagram, our custom code that performs business logic is in the Lambda functions. Our data is stored in DynamoDB NoSQL tables, although I think schemaless might be a better term to describe DynamoDB as compared to traditional relational databases. But the important point here is that the cloud platform handles the underlying infrastructure required for DynamoDB and other services. DynamoDB is highly scalable and highly available with minimal configuration required. Now I'll go through some lessons learned during our serverless journey. The first lesson is to embrace infrastructure as code. Anything that you can create through the Amazon console can and should be built with code. This is typically done in text files using a declarative language like JSON or YAML. With these files, you're expressing the desired outcome you're trying to achieve with your infrastructure. We used AWS CloudFormation, but Terraform and Cloudify are also nice alternatives. One of the advantages of using CloudFormation is the concept of stacks. Stacks treat your platform as a single unit with create, update, and delete operations occurring with atomicity. Everything succeeds or nothing does. The AWS Serverless Application Model, or SAM, extends the CloudFormation capabilities to make it easier and more seamless to write code for your serverless infrastructure. For example, there are templates for integrating your Lambdas with API Gateway, queuing services, or other cloud services. Treating your infrastructure as code allows for common coding practices like reuse, modularity, and change control through versioning. It makes it possible to go back to a previous infrastructure, or at least see what has changed. In a serverful environment, you may have stored credentials in the OS's environment variables. You may have even stored them in config files, despite the obvious security flaws of storing secrets in source control. With a serverless architecture, using a service like AWS Secrets Manager provides centralized management of sensitive values. These values can be encrypted and protected from unauthorized access using Amazon's identity and access management policies. The bottom line is that no plain text secrets are stored in your code or accessible to unauthorized subjects. We started out using Secrets Manager for our database credentials and API keys. After moving to DynamoDB, only the API keys were necessary. And these can be automatically rotated and integrated with your app without skipping a beat. For our system, we started out using a relational database service, or RDS, as our data storage. This was really because we already had a MySQL database and wanted to integrate it with our app. Using RDS set off a cascade of unnecessary complexities in our infrastructure. The primary issue was that it required our Lambdas to run in a virtual private cloud because of RDS's network interface requirements when controlling access. Running Lambda functions in a VPC exposed three key issues. We had no access to public APIs, including other AWS services like CloudWatch Metrics and Simple Queue Service. It exacerbates the Lambda cold start problem, which is a slight lag in start time when Lambda resources like containers are initially provisioned. The graphic here shows that the elastic network interfaces required by VPCs add to the cold start problem. Finally, managing a Lambda inside a VPC just isn't what we wanted to spend our time doing. It wasn't adding any value. Now, because this was a greenfield app, we had the ability to swap out storage from RDS to DynamoDB with relative ease. This may not be the case for others, but you should at least be aware of the issues that VPCs cause when using Lambda functions. Note that AWS Aurora serverless DBs must also be created in a VPC. Strive for repeatable and predictable deployments. There are several approaches you can use, but the most important factor is how much impact your customers can tolerate. You want to minimize disruption and have a process to revert changes. For our app, we didn't need to be very complicated, so we chose an all-at-once deployment approach. This simply replaces your current environment with your new CloudFormation stack. Other approaches like Blue, Green, and Canary shift traffic to a new environment while retaining the old environment in case of rollback. Our all-at-once approach takes on more risk since rollbacks aren't automated, but we can eventually use AWS Code Deploy to provide automated rollbacks. Depending on your situation, and especially in a live environment, you may need to use Blue, Green, or Canary deployments. Rollbacks are easier to initiate, but the entire deployment process can be a little more complex. No matter which deployment approach you choose, builds and test deployments should be triggered on every commit. We also used a separate code branch for staging and prod environments. We'll look at environment separation next. This lesson was a significant one because we really tried to use the built-in function versioning in both API Gateway and Lambda, but found that those tools didn't clearly separate the environments enough. There's a lot of discussion around multi-environment strategies related to serverless architectures, specifically in AWS. My concern with using a single Lambda or API Gateway instance for multiple environments was how easy it would be to misconfigure something and bring down or silently overwrite production. There's a great comment by an AWS engineer named Jacob Fuss that describes this as a bigger blast radius in the event that something goes wrong. The general approaches to the environment strategy boils down to single or multi-stack. We chose the multi-stack approach because clearly separate copies of each resource are created from the same CloudFormation template, driven by environment variables and dynamic parameters in the YAML file. The result is isolated API gateway, queuing, Lambda, and DynamoDB resources that are named appropriately for each environment. This allows for different config settings for each environment and clear isolation and a reduced blast radius. An additional isolation step would be to use different regions or AWS accounts for different environments, especially in production. For more details on what approach works best for you, I'll include some links at the end, or you can search for multi-environment serverless architecture. As a developer, there's a sense of accomplishment in building your own software. However, in a serverless environment, your job is more of a service integrator, leaving custom Lambda code to truly unique business logic or application processing. Lambda runtime is costly and precious, especially when executed at scale. Before writing a function, ask yourself if there are any other services available that can do this. One example is authentication. We defer to AWS Cognito for auth, but you might use auth providers like Okta or Auth0. Of course, they're not free, but you're offloading a common service to a platform that's really good at it. Plus, it's less code to maintain. Also, if you find that your Lambda function is simply transferring data from your API to storage, look for alternatives. For example, API Gateway allows for direct DynamoDB CRUD operations. It requires some complex configuration templates, but it's worth exploring as you scale up your platform and Lambda costs increase. You're no longer custom coding every aspect of your app. You're piecing together a puzzle of available services and custom functions. This isn't specific to serverless, but it's worth mentioning as you progress through your serverless design. You can still perform automated unit, system, and integration tests. In our case, we focused on unit testing and API integration testing. For unit tests, we separated our core logic from our Lambda handler function, which is the entry point to a Lambda function. By making the handler function sparse, you could drive logic with automated testing tools like PyTest for Python code. Ideally, these tests are fast and don't rely on external dependencies like AWS services. They're just testing core logic. For API testing, we designed our tests using Postman GUI, and then we exported these test collections into files that run on every commit. Our build pipeline runs both PyTest unit tests and Postman API tests on every commit. You should use Lambda layers for common code and dependencies. This is essentially a zip file archive that can contain custom code or common libraries like Python or Node packages. Layers allow you to reduce the size of your Lambda deployment package and reuse common code across functions. Another simple technique is to include multiple related Lambda functions in one code file. This results in multiple handler functions in the same file, but it also allows you to reuse common functions across multiple Lambdas. Each of these techniques can be used for different situations. For example, custom code that's common across most of your platform can be added to a layer, while code that's common amongst a small set of functions can be added to a single file. Lambda lifecycle consists of an init, invoke, and shutdown phase. The init phase is when the execution environment is created and resources and code are downloaded. This is also when the runtime is initialized and the code outside the main handler is called. This phase is the source of the infamous cold start issues that you may hear about. Init phase is only invoked when the Lambda function is shut down after not receiving any invocations for a period of time. This is where connections should be instantiated. The benefit here is that they can be generated during the init phase and then reused for subsequent invocation calls to the Lambda handler function. This is a simple way to recover function execution time and save costs on your Lambda functions as they scale up. This technique applies to both AWS service and RDS connections. Although we ultimately moved away from using RDS for storage, if you can't avoid it, I'd recommend taking a look at Amazon RDS Proxy. This resource sits between your Lambda and RDS and efficiently manages connections, much like a classic connection pool. The Thunder blog has a nice article on managing RDS connections within Lambda functions. As we built out our architecture for the pass-to-play environment, it became clear that it's just easier and cheaper to embrace the services available within AWS, especially if you're developing new apps and not constrained by legacy, compute, or storage resources. Data transfer between Lambdas and most AWS services is free. Security integrates nicely within the AWS IAM system. The code pipeline, automated build, and deployment system also provides seamless DevOps functionality. Embracing AWS so much wasn't a problem for us, but may be risky for other organizations or products. There are vendors that promise cloud agnostic architectures, but they rely mostly on containers, which add another level of complexity. Also, you may end up relying on the cloud agnostic vendor, essentially locking into them too. I'd recommend looking at tools that try to abstract away the cloud platform as much as possible without losing too much functionality. Terraform is an open source infrastructure as code software tool. We didn't use it, but it's worth considering their configuration tools. To summarize, here are some common concerns that people have with serverless. Vendor lock-in. We've discussed vendor lock-in, and my advice is just to realize that most solutions have some level of vendor lock-in. Oracle has been taking advantage of this for decades, and so has Microsoft, especially with their Office 365 suite. But then again, a lot of successful companies have thrived on tools by these vendors. This is not an endorsement of either one of them, but just a point about doing what's best for your situation. If you embrace AWS, Azure, or GCP, how easy would it be to migrate your core applications from one cloud to another? Be aware of the risks of such a move so they can be weighed against the motivations of moving from one cloud platform to another. And sure, containerization is a good way to avoid locking into the major cloud providers, but just be aware of locking into other container-based vendors. AWS and other cloud providers are constantly looking at ways to make pricing more transparent and predictable. Of course, the whole point of pay-as-you-go is that it's not predictable. But you can take advantage of compute savings plans with Lambdas that offer 10 to 15% savings in exchange for committing to a consistent amount of compute usage for over 1 or 3 years. They also introduced duration billing at the 1 millisecond level rather than the previous 100 millisecond level, and this can save a lot of money at scale. Remember that both AWS and Azure offer 1 million executions and 400,000 gigabyte seconds of execution time per month, per function. Gigabyte seconds are the number of seconds your function runs for, multiplied by the amount of RAM memory consumed. And finally, the cold start problem. There are several ways to mitigate this problem, depending on how much time and money you have. Use provisioned concurrency if cost is not an issue. Use the fake request technique to periodically call functions if you don't mind managing another function. And we've already discussed avoiding VPC use whenever possible. So was it worth the time and money? For us, the answer is yes. We set out to build an architecture that was very low cost and with little infrastructure management overhead. There's a learning curve with automated builds, YAML files, service integrations, and security roles, but it's worth taking the time to evaluate the tools that are available and constantly changing. I've found that the biggest benefits as we ramp up our product are the low monthly cost of the pay-as-you-go model and not having to install or maintain an OS, web server, or server firewall. We're a team of developers. Our skill set and strength is coding and not infrastructure or network engineering. And serverless architectures allow for widespread automation, leading to predictability, especially when your app is rapidly changing. So finally, here are some helpful links that address some of the issues that we faced. Good luck with your cloud journey, and I hope you learned something useful about going serverless.